In the first question, electric conduction in a semiconductor takes place due to obviously both electrons and holes. In the next question, an electric field is applied to a semiconductor. Let the number of charge carrier be n and average drift speed is v. What will happen if the temperature is increased? On increasing the temperature, we know that a huge number of electrons will come into conduction band and the conduction electrons will increase exponentially. So n will increase exponentially, due to which the rate of collision will also increase. There will be more frequent collisions and relaxation time will decrease. Obviously, the average time interval between two collisions will decrease. So Vd will decrease, but still, as the number of electrons has increased exponentially, the current will increase to a very large extent. In the next question, there are Np and Ne with the number of electrons and holes in an intrinsic conductor. So as an intrinsic conductor, the number of electrons and holes remain same because every bond that breaks contributes to a single electron, free electron, which is called conduction electron, and a hole also. But in the question number 4, there are if the conductor is extrinsic, depending on its type, whether it is n-type. If it is n-type, then number of electrons, conduction electrons, will be more than number of holes. Similarly, if it is p-type, then number of holes will be more than number of conduction electrons. So they will not be equal, and A and C both can also be correct, but as this is a single option correct, we'll go with option D. In p-type semiconductor, as we are transferring atoms, again, while doping we transfer atoms, not just the nucleus or just charges. We are transferring the whole atom, so we are not transferring any net charge. So the p-type semiconductor or n-type semiconductor will be uncharged no matter what the temperature is. In question number 6, when an impurity is doped into an intrinsic semiconductor, the conductivity of semiconductor will obviously increase. That's why doping is done. Okay, so we are adding pentavalent or trivalent impurities. So by doing that, we can increase the number of conduction electrons or free holes to a very large extent, thus increase the conductivity. So option A will be the correct answer. In 7th, if the two ends of a PN junction are joined by the wire, what will happen? There will be a current which is not steady in the circuit for a very short duration and it will die after all. Then the drift current in the PN junction is we have to find that what is the direction of drift current in the PN junction. You can look at this diagram. So this is P side. The circles are basically holes and there are few conduction electrons also, but majority will be holes. And this side is n-type. The darkened dots are basically electrons, conduction electron, and this one is a hole. Okay, so as these were electrically neutral before, but because of diffusion, the holes will transfer to this side and electrons will transfer to this side, and near the interface or near the junction there will be a positive and negative charged volume. This side will be charged negatively and this side will be charged positively because of the holes which are coming from this side and electrons which are going to this side. So as we can see that diffusion is from P to N for holes and from N to P for electrons. So the diffusion current in both way will be towards P to N, and the drift current is nothing but from N to P. Okay. So in the next question, they are asking about what is the direction of diffusion current across the PN junction or the drift current. I have already explained. In the next question, diffusion current in a PN junction is greater than drift current in magnitude. Obviously, diffusion current will be maximum when the biasing is forward biasing, and drift current will be more than diffusion current when the biasing is reverse bias biasing. Okay. In question number 11, two identical PN junctions may be connected in series with a battery in three ways. And we have to find the potential difference across the two PN junctions will be equal in which of the following case. Okay, as we already know that if the junction PN junction is forward biased, it acts as a very low resistance, and if it is reverse biased, it acts as a very high resistance. So we can replace them by low and high resistance depending on their biasing, and the diagrams will look like this. In the first one, the first junction is a forward biased, so it will be a low resistance and it will be a high resistance. So obviously the current will same, so will not have same potential difference across a low and across a high resistance. And if both are low or both are high, obviously the current is same. Again, the point is current is same. The both are low and both are high, so we'll get equal voltages in this diagram also and in this diagram also. So in second and third, we'll have same potential difference across the diodes, but in case number one, the potential differences will be very different. Forward bias will have a very small potential difference and reverse bias will have a very large potential difference. In question number 12, two identical capacitors A and B are charged to the same potential voltage V and are connected in two circuits at t equal to 0 as shown in the figure. Then the charges on these two capacitors after a time t equal to RC. We have to find the charges on these two capacitors at t equal to RC. So as we know, this diode is a forward bias because it is connected to the positive terminal like this, and this is a reverse bias diode, so it will offer a very high resistance and this will offer a very low resistance. So for this capacitor, the equivalent resistance will be very close to R, which is because this will act as a zero resistance, and for this capacitor, this will act a very high resistance and the equivalent resistance will be very high. You can also look at this diagram. This is a forward biased, this acts as a zero resistance, and this is R. So time constant is nothing but RC. But in this case, as this resistance is very high, so we can say almost tending to infinity, time constant will be R equivalent, which is R plus infinity into C will also be infinite. Hence, the general equation of charge while decaying is given by initial charge Cv e to the power minus T by Rc. In this case, T by tau. And we can say if T is equal to Rc, we can say it will be Cv by E. But in this case, as the tau is infinite, minus T by infinity will give you 0. E to the power minus 0 is nothing but 1. So the charge is Cv. It means it will not discharge. So the charge will remain same, but it will discharge like a normal capacitor. So the time after time t equal to Rc, the charge will be decreased to Cv by E. Okay, so B option is correct. The charge on first will be Cv by E and on the second will be Cv only. A hole diffuses from P side to N side in a PN junction. This means actually a hole is nothing but a vacancy created by an electron when it broke its bond. So When a hole diffuses from p side to n side, there must be a bond which is broken in n side. Because of that, an free electron and a hole is created. And that electron from n side must have jumped to p side and formed the bond. Okay. Again, an bond will be broken in inside. Because of that, a free electron and free hole is generated. And as we have to decrease the hole from p side also, that electron will jump to the p side and form the bond with the hole and just vanish it. So the hole will be created in inside hole. Okay, and that is option C only. In a transition, in a transistor, the base has the least concentration of the impurities, as we already know that, because we don't want much of the emitter current is absorbed or taken by base. Most of the current should pass to the collector. That's why has the least concentration of impurity or least doping. In this incomplete statement about the transistor, the emitter base junction is forward biased and the collector base junction is reverse biased, and emitter base and collector base, so both are phase base for normal working of a transistor. Okay, thank you.